In this lecture, we'll learn what causes solar activity and how solar activity affects us humans and how it varies over time. The energy generated in the sun's core eventually reaches the solar surface where it helps create a variety of phenomena that we can observe from Earth. We call these changing features solar weather or solar activity. Solar activity is like weather because it changes with time. Solar activity features include sunspots, huge explosions known as solar flares, and gigantic loops of hot gas called prominences. All of these phenomena are related to magnetic fields. Sunspots are regions that are about 2000 Kelvin cooler than the sun's surface. They appear dark relative to the brighter photosphere that surrounds them, but if you could isolate one, it would be blindingly bright. They are cooler because magnetic field lines suppress convection within the sunspot and prevent surrounding plasma from entering the sunspot. With the hot plasma unable to enter the region, the sunspot plasma becomes cooler than that of the rest of the photosphere. Sunspots typically last up to a few weeks, and they dissolve when their magnetic fields weaken and the hotter plasma is allowed to flow in. Sunspots tend to occur in pairs, connected by a loop of magnetic field lines that can arc high above the sun's surface. Gas in the sun's chromosphere and corona can become trapped in these loops, making giant solar prominences. Some prominences rise to heights of more than 100,000 kilometers above the sun's surface. That's about 8 Earth diameters. Individual prominences can last for days or even weeks. Like sunspots, they disappear when the magnetic fields finally weaken. The magnetic fields winding through sunspots and prominences sometimes undergo dramatic and sudden changes. This produces short-lived but intense storms on the sun. The most dramatic of these storms are called solar flares. It's thought that flares occur when the magnetic field lines become so twisted and knotted that they can no longer bear the tension. They suddenly snap and reorganize themselves into a less twisted configuration. Enormous amounts of energy are released in the process. In this ultraviolet image of the sun, we can see dark spots called corona holes. Corona holes are places where the sun's magnetic field opens up and allows the solar wind, that stream of charged particles, to escape. Solar activity can affect us humans on Earth. For example, solar flares can sometimes launch 1 billion tons of superheated gas into space. These particles travel outward from the sun in a huge bubble called a coronal mass ejection. Coronal mass ejections can create geomagnetic storms that disrupt electricity and communications on Earth. Geomagnetic storms are also responsible for the beautiful aurorae. When the charged particles ejected from the sun strike atoms and molecules in the Earth's atmosphere, they excite those atoms, causing them to light up. Solar activity does vary with time. For example, the number of sunspots on the sun gradually rises and falls over an approximate 11-year cycle. We can see that the sunspot cycle can differ each time. Sometimes there are lots of spots, sometimes there are fewer. At each solar maximum, the sun's entire magnetic field starts to flip, turning magnetic north into magnetic south and vice versa. This graph reconstructs the sunspot cycle over the past 400 years. Longer-term observations hint that the sunspot cycle can change more dramatically. Between 1645 and 1715, there were virtually no sunspots. This so-called Maunder minimum could be part of a longer-term cycle, or it could just be a fluke. The precise reasons for the sunspot cycle are not fully understood, but the leading model has to do with magnetic fields and the sun's rotation. We can imagine what happens to the magnetic field lines that start out running north to south. Because the sun rotates faster near its equator than at its poles, the field lines bend ahead at the equator. The field lines become more and more twisted with time, and sunspots form when the twisted lines loop above the sun's surface. Well, that's all for the sun chapter. Now that we've studied our own star in some detail, we can apply what we've learned to the other stars in our galaxy. We'll get to the properties and patterns of stars next time. Take care. I'll talk to you soon.